2024, question 36. Consider a steady, fully developed, unidirectional. So this is my direction of flow, laminar flow. So this is a laminar flow of an incompressible Newtonian fluid. So that makes life easy between two infinitely long horizontal plates. So this is my top plate and this is my bottom plate, separated by a distance 2h. So we just go here, y is equal to 0. This is y is equal to h, and this is y is equal to minus h. So the difference is force 2h. The flow is driven by the combined action of a pressure gradient. So here is the pressure P1 and here is pressure P2. And also it says that P1 divided by L is P1 minus P2 divided by L is greater than 0, which really basically means that P1 is greater than P2. So this is a pressure driven force. So this is the way in the x direction the fluid is flowing. Here are the points, okay, distance L. So here is the P1 minus P2. So basically, this is the distance. So the distance between the two is L, okay. Um, the bottom plate has a velocity of magnitude v with respect to the stationary top plate at y is equal to h. So this is a stationary plate. So here velocity v is 0. It's not moving. So this is a plate which is not moving, and whereas this is another bottom plate which of course is moving but in the opposite direction with a velocity v. So that's why it's not a fully developed laminar flow. It's laminar flow up to a certain point and then it goes in the opposite direction. So this is the one. Okay. This two being stationary, of course, in the case of laminar flow, we have to find out which one of the following equations represent the x component of the fluid velocity vector. So this is my x, and this, of course, is my y, and this direction, of course, is z. Okay. So let us take a better look of this situation here. So this is my plate, top plate, and this is my bottom plate here. This is pressure P1, this is pressure P2. The fluid is flowing in this direction, and this is a Newtonian fluid. As I mentioned, this is y at y is equal to plus h. Velocity v is equal to 0, and at y is equal to negative a, velocity is negative of v direction. And this is my x direction, this is my y direction, and this is my z direction. So we have to apply the Navier-Stokes equation in the x direction, which is given as this one here. Now, let us quickly look at each one of these points. Before that, let's look at the velocity vectors. So Vx, that means the velocity of the fluid in this direction, is not a function of x. That means whatever it's a constant velocity is moving in this direction. It's not a function of, but Vx is a function of y. So whatever the velocity in between the two plates, so the velocity of the fluid is here at certain y is in this value, this value. So as you can see, and of course here the velocity is 0, and here of course the velocity is negative v because of no slip condition. So the velocity of the fluid Vx in the x direction is a function of if y. That means in y direction, the velocity vx changes continuously from negative v to 0. So as I said, vx is a function of y, but vx is not a function of z. That means in this direction, we are assuming there is no variation of the velocity. Whatever velocity here is the same everywhere. So it's not a function of Vy is equal to 0. That means in this direction the fluid is not moving. The fluid is moving only in this direction, in unidirectional. So Vy is equal to 0. And of course in this direction also there is no flow. So we will say Vz is also equal to 0. If we take that, so therefore this would be equal to 0 because this is a steady state condition, time invariant. And as I have said that this is not, so since Vx is not functional, so this is going to be equal to 0. So since this is not a function of x, Vy is 0. This values of course has a certain value, but since Vy is equal to 0 here, so therefore this term also would be equal to 0. And since Vz is also 0, so this term puts out to 0. So the entire substantial derivative here, this entire thing is equal to 0. This negative del P by del X of course remains because it's a pressure driven flow. And of course, this is the viscosity. And since this is not a function of Vx, is not a function of, so this second derivative would be equal to 0. This term, of course, will remain since Vx is a function of y. Again, Vx is not a function of z, so this term would be equal to 0. So what we are left with here is, as we can see, that 0, this part on the left hand side, as I said, the entire substantial derivative is equal to 0. So entire left part is equal to 0. This is equal to negative of del P over del X. And of course, this is given as, we can say, P2 minus P1 divided by L, okay, if we assume that to be constant, and this is mu, and this term of course remains. The rest of the terms are equal to 0. So we're writing this as negative of P2 minus P1 divided by L, the final. So y del P, this would be called the final minus initial. So that way we write it, and this is the second derivative. Okay, so and as I said, the v is equal to 0 at y is equal to plus h. This is stationary, and y is equal to minus h. This is equal to negative v. So if we go to the next part, so this is my equation here, and if we write that, make the integration, we get of course two constants here because this is the second derivative. So details shown here, details shown here. Minute. Details shown in here. How do we come here? And of course, there's a boundary condition, as I said, at y is equal to plus h, vx is equal to 0 because this is a stationary plate, no slip condition, and y is equal to negative h. This vx is equal to negative v, moving in the x direction, and negative x direction. Of course, again, no slip condition. Okay, so if we do the final integration, we'll find that this is, of course, the relationship here. That's what we get, and we, of course, that corresponds to this part a, which is true. Okay, so let's quickly see if A is true, how do we make sense out of it? In fact, in the website here, we have taken each of these and shown that these boundary conditions satisfy only this one. So let me show how that really happens. That if we start with the momentum still balance, then the shear from the shear stress, we can arrive at the same equation here. We have shown that in the website here. Anyway, okay, so let's quickly see how A actually satisfies. So y is equal to plus h. We have shown that v is equal to 0. Let's see if that happens. So so this is my vx is equal to, so as you can see, at y is equal to plus h, at plus h, this of course is going to be equal to 0, because this is plus h square by h square, so that would be equal to 1. So this term would be equal to 0, and y is equal to plus h, this term is also equal to 0. So it satisfies that at y is equal to plus h, vx is equal to 0. Now let's see what happens at y is equal to negative of h, which is this one here. So if we take negative of h here, of course, negative of h whole square, and that of course this term would be equal to 0, but this one would be v over 2 divided by, this would be equal to v over 2 divided by negative of 2. So these two cancels out. So we get y is equal to negative of h. We say vx is equal to negative of v, which is this one right here. So here Vx is equal to negative of V, and here Vx is equal to 0. So A satisfies the boundary condition. So again, this is the correct solution.